in Bohr's model for the hydrogen atom, you eventually find that the energies of the electron in the atom are quantized. But you do that in a kind of a classical way. You start with assuming that the electron is in a circular trajectory around the nucleus, that the centripetal force of this motion, of the circular motion, is the Coulomb interaction between the electron and the proton in the nucleus, and then you say that the angular momentum is quantized. This leads to quantized values for the radius of the orbit, and eventually this will lead to energies that are quantized, like minus, for the hydrogen atom, that would be minus 13.6 electron volts over n squared. And this constant here is what we call the Rydberg energy, right? So here what I would like to do is to find the same result, but now using Schrodinger's equation. This will provide more information about the system. So this, in Bohr's model, you find information about the energy, but now in Schrodinger's quantum mechanics, solving Schrodinger equation for the hydrogen atom, now you are going to have also information about the atomic orbitals, like the sp, d orbitals in the atom. So in order to do that, you have to start with Schrodinger equation. I'm already writing the time-independent Schrodinger equation, as you see here. So the Coulomb interaction is going to be something like this. And here I'm going to use coordinates that I'm going to call like r bar here. These are coordinates that have a unit, just because afterwards I'm going to write a dimensionless unit that I don't need to write the bar all the time. So that's going to make things easier a little bit. I will explain this further on. So now I have this psi here, and then I will call this E, I will call it E bar also, because afterwards I'm going to write an E that has no unit, and then I'm going to keep writing this E without the bar. It's going to be easier for me. So the equation is going to be something like that. Notice that I use here the electron mass. Where is the nucleus mass then? Actually, as the nucleus is very heavy, I'm already assuming that it will be the electron that is moving, and the nucleus, it's going to be stopped or slowed down as compared to the electron. You can also see that mathematically. If you want, you can write this problem with electron and nucleus coordinates, and in this case you can separate coordinates into the relative and center of mass coordinates. This one is a relative coordinate, for example, between the electron and the nucleus. And if you separate coordinates like that, you see that there will be a term for the center of mass, and this term you can separate from the equation and so on. And then the other term would be with something that is called the reduced mass of the electron and nucleus system. But the problem is the mass of the nucleus is much heavier, and because of that the reduced mass is basically just the electron mass in the end. So that's going to be okay just to use electron mass here. So I'm also going to use something like, you have this thing here. If you get all these parameters here and you work a little bit with them, you see that they are the same as being the Rydberg energy multiplied by the Bohr radius to the second. And in this one, if you work a little bit with these parameters, you see that this is the same as 2 times Rydberg A0. And then I will use A0 as the coordinate of space, so as the unit of space coordinates. So this is something like, I put A0 on the bottom of this R bar now. So right now I'm going to write R is equal to R bar over A0, right? And then also here is the second derivative, so there will be like two special coordinates here, so I need to put this on the bottom here. Then in the end I'm not going to write this A0 anymore. This is included inside the units of my calculation. Now I divide every term here by Rydberg energy too. Then in the end I have this is something like this, right? And now this thing here, or actually the negative of this, I'm going to call E. E is going to be minus E bar over Rydberg. Why minus? Because I know that these energies are going to be negative. I'm looking for the bound states. The bound states would be with negative energy, right? So in the end, if I rewrite this equation, I'm going to have something like minus Laplacian, but now the Laplacian is written in these units. These are like dimensionless units. Then psi minus 2 over r. Then I'll have this minus e. It will end up as being plus e on the other side here, and this is equal to 0. So this is actually my new equation. It has a lot less parameters to be worried about, right? So now I have this Laplacian here. The Laplacian, I'm going to write it in spherical coordinates. So in the end, this is supposed to be something like 1 over r squared. And there will be also a term which is with the angular coordinates. It's going to be something like this. Oh, here actually the derivatives should be all be partial derivatives, right? Because I still have a function that has more than one coordinate here. So actually this is partial like that. Now this is something like this. And then I'll have let me write the whole equation here. I will multiply by minus 1 the whole equation, then I will have something like plus 2 over r psi and minus e psi, right? Okay, so for those who are not familiar with the separation of variables, then what I'm doing here now is I want to propose a solution in this form: r theta and phi. This is going to be a capital R, which is just only function of r. Then you have capital theta, just a function of theta, and phi, just a function of phi. And or actually I can already group these two into a single function. This is going to be enough for what I'm doing now. And in another video I will explain this better, but these are exactly what we call the spherical harmonics. So now that you have a function like that, you can substitute here, and then this is going to be something like, instead of psi, I'm going to write r. And then you see that here there is a derivative in r, so I could put these other functions just here, right? I'm going to use the y function here. I will put y here, and also in these coordinates I only derive the theta function, so the theta coordinate, so I can have a r here, but here I will put a y, because I still have to derive this y. Then also here it's the same thing. I can put an r here outside of the derivative, but inside the derivative there is still a y function here, because I still have to derive it. Here I can have just the multiplication between these two, and also here. So now the next step is to divide every term here. I divide it by 1 over ry, right? So, or I multiply by 1 over ry. So I divide every term by r multiplied by y. If I do it like that, I will cancel this y, and there will be a r here. Now here I will cancel this r, and there will be a y here. I'll cancel this one, there will be a y here. I will choose to cancel only the y here, or only the y function here, or I can cancel both. I will put like r and y here in the bottom, which should cancel this and this, right? And now what I have is I have a term, or I can also actually I can still multiply everything by r squared, because this, you're going to see why this is interesting right now. If I multiply everything by r squared, then this term doesn't have r squared anymore. This one doesn't have r squared. This one it will have a r squared here and an r squared here, right? And so, and this one, it will also cancel this r squared here. Okay, so what is the conclusion of this whole procedure now? Is the fact that this term, along with this one and this one, they only have r coordinates in it, while this other term here, or this collection of terms here in the middle, they are a function that is for sure a function only of theta and phi, while these two together, this and this, I'm gonna call 1 and 2. These two terms together, 1 plus 2, they will be a function that is for sure just a function of r. And I'm saying that the sum of a function of r with a function of theta and phi is equal to 0. So this is only possible if I say that separately each of these terms is a constant. So in the end, this first term here, this g of theta and phi, it needs to be exactly a constant. And this constant, I will actually write it in a very convenient way as L plus 1. And this other one, I will rewrite also this constant as minus L plus 1. And, or actually, it's the opposite. This one needs to be minus, and this one needs to be plus. And this is related to the fact that I want later on to connect these g here and this term of my equation to the spherical harmonics. I will do that in another video. But in the end, again, what I'm saying in summary is this is a function only of theta and phi. From the equation, I see that. The other terms, 1 and 2 here, they are a function only of r. And the sum of them is 0, which means that g needs to be a constant, because if it is not a constant, then it's variable and it has to change with theta and phi, while the other function changes only with r. So how can you make it always equal to 0, this sum, right? So that's why I need to separate these two things and into constants, that when I sum these constants, they are equal to 0. So now this is a primer on separation of variables, right? So now I'm going to as I said, I'm going to make another video about these angular coordinates. Right now I'm going to focus only on the radial coordinate. So how is the equation for the radial coordinate now? It's going to be something like 1 over r. I'm going to put the r squared back here, okay? Then there will be an r coordinate here, and there will be another term which is minus there is a term that is 2 over r minus e r, and now there is this should be equal to L plus 1 over r squared, right? So this, I can put this thing in the other side of the equation here. I would just like raise this and say that this is equal to 0. Okay, so I'm going to make something else that makes the equation easier to deal with, and this is going to be I will replace r by an auxiliary function u over r. Why is that? That's because if I derive this thing, then I'm going to find something like I can derive u over r, and then in the other term I'm going to find something like 1 over r squared u, right? If I derive 2 times this, then I'm going to find, I can make it something like this, then plus 2 times u and r to the third. This is first timer is like I keep 1 over r and derive 2 times the second function, which is u. Then I keep u and derive 2 times 1 over r. Now I make it plus 2 times derivative of u derivative of 1 over r, which gives me 1 over r squared, and there will be a minus function here instead of plus, right? So now I know how these derivatives are, but this first term here is 1 over r squared These actually can be written like this, right? And then if I rewrite using the u function, then this is going to be something like, I'll just make it equals to, so this is the same as u derive it 2 times, then u, but all these terms, all these terms, they are like this, they are okay, but the other terms I have plus 2 over r multiplied by the first derivative. So then I'll have plus 2, then here it's going to be r squared, and the other one is going to be 2u over r to the third. So did this help? Let's see. This term here will cancel out this one, and this term will cancel this one, and now I have only one term. So my equation that had like this bunch of derivatives, now it's going to have only one derivative there, so it's going to be much easier to deal with. So my new Schrodinger equation now, it reads something like this. 1 over r second derivative of u, so this is my new equation, right? And there will be nothing else in the derivatives here, but now I have plus 2 over r minus e. Here I should put r, I'm going to put u over r. Oh, there should be a r here too, right? Of course. So now I can multiply everything by r, and then I will lose this, and now I have an even simpler equation to solve now. So the equation I really need to solve is this one. So let's start solving this equation. One thing that I can do also to help with my solution is to look for asymptotic behaviors of these functions, right? So let's see what happens if I make r going to infinite. So if I do it like that, then I will have an equation, like a effective equation that is more like d squared dr squared u, and then I have this minus e u, because the other terms will all be practically 0 because r is going to infinite, right? Then I can just put this term to the other side, then I have e u, and a clear solution for this thing is to say that u is in that regime, it is approximately an exponential. And I need to say it's an exponential decay actually. So, and this is a second derivative, so this should be square root of e, right? Square root of e r. Then there could be also a plus square root of e r, but then if I do that, I'm saying that this function is going to grow exponentially with r, and this is not what we want physically, right? So we want to avoid exponential growths there, because the function needs to converge to 0 at the r going to infinite, right? So now this is one behavior, at least for r going to infinite, this is what we get, and just like keep that information. Now let's see what happens if r goes to 0. In that case, what we have is we have d squared dr squared u, and what I'm going to put, like even in the other side here, is there will be other 2 terms that will be more relevant. For example, this term here actually is going to be the one that is more relevant compared to the other ones, right? Because it has r squared in the bottom. So this is going to be the largest term between these 3. So here I can do it like that. Oh, sorry. Then L plus 1 U, right? So one way to solve this thing here is to look for a solution in the form of U is equal to R to the lambda. And then let's see what are the conditions for lambda for that to occur. So let's see, you have second derivative, there will be this is the left side, and then in the right side I have L plus 1, and here I have still the R lambda minus 2, right? Oh, actually I forgot to put an R squared here. And then as I have R to the lambda here and a R squared in the bottom here, actually this is R to the lambda minus 2, and this is going to cancel out this other term here. Then that's fine. So if I say that lambda minus 1 is equal to L plus 1, then if I find the lambdas that solve this equation, then these lambdas can be put here. And actually, you can solve this equation. It's a second order equation. It's a normal equation. It's easy to solve. You see that there will be two solutions. One is going to be minus L. The other one is going to be L plus 1. And we have to avoid the minus L solution, because this is a solution that is 1 over R, in a sense, actually 1 over R to the L. So if R is going to 0, then this solution here will also diverge. So I need to say that in this regime, U is actually approximately R to the L plus 1. So now, finally, what I have is a new U, that is U of R, that I want to say that this is actually something like exponential of square root of E, R to the L plus 1, and then a V, another auxiliary function, something like that. Okay, now let's put this equation here into Schrödinger's equation for the hydrogen atom and look for what is the effective equation for V. This is what I finally need to solve as a differential equation. So in order to do that, I need to find what is the second derivative of U in this form, because this is the left side of this equation here, right? The left side of this equation, or actually it's this term here, right? So this is the only derivative term that I need to care about. The other ones I can add later on. So this second derivative here, it is, you can make that trick, like derive one function and keep the others and so on. So what we're going to do here is I make second derivative of V and keep the other functions. Now I make second derivative of the exponential and keep the other functions. This is going to give me E. And now second derivative of the power function. Oh, sorry, there should be an exponential here still. Then the second derivative of this power function here is going to be L plus 1 L and the power function. Right? Now I will have three terms like that, and also some mixed terms like plus 2 times I keep R, then I derive the exponential, and V. Now I make another term where I keep the exponential, then I derive the power and V. And now I have a last term, which is I keep keep V, and then I derive the exponential and the power. Okay, so this collection of terms is what is going to give me the second derivative. It's very tiresome, but if you do it, it's not hard, it's just tiresome. So then in the end, I can even put some terms together here to write what should be this derivative here. Let me write it like this: r to the L I'll do it like this, and then let's put all the terms together here. So the term with the second derivative here should be RL plus 1, so there should be an R here, and second derivative of V. Then this is exactly this term here. Now there will be a term with the first derivative. There are actually two terms like that with the first derivative. There is one like this and one like this, right? So these two terms, if I put them together, they will read something like the first derivative, and they will multiply in this one. It will multiply something like 2. I will actually put this 2 in front of it. Then in the first term there will be something like L plus 1, and RL is already there, and there will be another term which is minus square root of E, right? And there must be a R here also, because here this is just L, and in the exponent here there's L plus 1. So this is okay. Now let's put together all the terms that multiply only V. So these terms are this one. So the exponential is already there. There will be an E and an R, right? So that should be RE. What else? There is this term here. This exponential is already there. This term I have to put there. And this should have 1 over R on it. So there must be a term like this, and there must be a L here too, right? And the last term is this one. So there is this exponential is already there, R is already there, so it's just like this 2, this square root, and this term here. So this is my equation. Believe me, this is going to make things easier in the end. It looks not so nice right now, but it's going to help in the end. So now if I look at my equation like this, I can put this term here to the other side and compare the second derivative to what I have in all of these things here. So let me do that. So this second derivative is already what I have here, and let me just take note of this here also, just again in this page, just for completeness. And the right side of the equation has to read like this, right? So it was supposed to be something like this. Let me write exactly as we did there. So this is with R squared, this is R, and this E has nothing in it. And then it should multiply the U function, but the U function is actually R to the L plus 1 E to minus square root of E R V. But we don't want this thing here because I didn't put it here, right? So because of that, I don't have a power of 2 here. I don't have this R here too, and there should be R here. Okay, if I do it like that, now this term will cancel this one, and this term will cancel this one, and also these things here will cancel here too, is these two functions. Actually the v, of course, it stays. But now finally my equation is actually like this. So here the only term that is kept is there is this 2 multiplied by v that comes from the other side here. Then it's now 2 minus 2 L plus 1. So this is equal to 0. So just notice that these 2 here is actually this one, and this term here is actually this one, right? So this is the equation that I have to solve, and in order to solve that, I'm going to go for a solution that is in the form of a series, a power series. So I'm going to make like a summation over j, cj, r to the power of j. I'll get something like that. So if I just substitute this thing here in the equation, a solution like that, then I will have something like its second derivative here. I will have this cj, will be a sum in the first term, then cj, then I will have j minus 1, and then r to the, there should be j minus 2, but then there is an r here, right? So because of that, instead of being j minus 2, now this is j minus 1, right? And for the second term, then I have this sum here. Then I have one derivative, so there should be a 2 here because of this 2 here. But in the first term here, I don't have an r, so I just use like L plus 1, which is this one. I make a first derivative, then I have a j here, r to the j minus 1. This is all. For the second term, I have minus 2 square root of e. Then I have the derivative, so there will be also sum in j, cj. I derive it, there will be a j here, and r. There should be j minus 1, but there is an r here, so this is just j. And then finally, this last term here, which is simply plus sum in j of cj, and this has to be equal to 0. So now I want to keep all the powers that are in the same order. So in order to do that, if you are not familiar with power law, with power series solutions for differential equations, I suggest you go for some mathematical physics books, for example. They have some explanation for that. But here what I can do is, since this sum here is done over all possible values of j, I can just start this sum here at a point that would be something like j plus 2, for example. And I will do the same here too. Like, I mean j plus, j I can replace j by j plus 1. Then also here I will replace j by j plus 1. And this is just as the same as the starting this series at a later point, something like that. So if I do it like that, I can already rearrange the terms in a way that I have c, now j is j plus 1, then this j plus 1 like this here, and this first j is now j plus 1, j minus 1 now is just j, and the power here is just r to the j minus 1, but now j is j plus 1, so this is just j, right? Then there will be another term which is 2 times cj plus 1, and r to the j, something like that. Then there will be a third term which is 2, and finally the last term which is I can put a 2 in front of it here, and 1 minus and this is equal to 0, right? So all these terms of the order of that multiply r to the j, they should sum and be 0. So let me collect these terms in the other page here so that we can see how they go then. So that's how the terms go. Now, if this is equal to 0, then I'm able actually to isolate Cj plus 1 is equal to Cj. Then I have 2 square root of e minus 2 minus I have something like this. These are all the terms that multiply Cj here, for example. And then in the bottom you have something like this. Actually, this term in the bottom, you can even rewrite it in a more in a better way. You can put j plus 1 here, and then you put like j plus 2 l plus 2, right? You can do it like that. So right now, what you need to see, and I'm not going to demonstrate here, but what you need to you can try yourselves there. If I let this sequence of powers in the series go all the way to j going to infinite, this thing will give me the expansion of an exponential function, and it's a positive exponential function whose argument is larger than my exponential function, like that one, like this one that I use it as the asymptotic value. So what I'm saying is, if you leave this, if you let this this power expansion go all the way to j going to infinite, you are going to have a function that diverges. So this means that I cannot accept a solution where j goes to infinite. I cannot have a solution like that. I have to truncate this series somewhere. So I have to stop the series somewhere. So in order to stop the series, then I have to find something like Cj plus 1 has to be 0 at some point. And how do I get that? If I do 2j square root of e minus 2 minus... If this is equal to 0, then I truncate the series. I stop the series at some point, right? But if I do it like that, I can also like cancel this thing. What is the condition for that to happen? Then the condition is that square root of e has to be something like, I can put this 2 on the other side here, which is now 1, like I divided it, right? So it's going to be 1 over, now I have j plus l plus 1. And then I make this thing squared. This is going to be 1 over j plus l plus 1, which is actually j plus l plus 1. Remember, what are these numbers here? These are all integer numbers, because this is the order of a polynomial. This is the L that comes from the spherical harmonics, and this is just an integer, of course. This is just 1. So in the end, I can rewrite my solution as being something like E is equal to 1 over n squared. But remember who this E was in the beginning of my calculations. If you go like back here, this E is minus the energy over Rydberg. So let's see. E is equal to minus the actual energy over Rydberg, which means that the actual energies are actually minus Rydberg over n squared, which is exactly what I get from Bohr's model, which is a lot simpler than that, right? I mean, it's just like a circular motion of an electron. So here I get a solution that in terms of energies this is the same as in Bohr's solution for the hydrogen atom. What is the extra information that I get from here? Is that this n is not really just an integer. It's not as simple as that. This n has a rule for it, right? it has to come from something like that. So what I'm saying now is that n has to be something like j plus L plus 1, which means that if I choose the quantum number n to be equal to 1, which is my first solution, it becomes mandatory that the function that I have has j equal to 0 and L equal to 0, because remember that this L comes from the spherical harmonics, it cannot be negative, and this j is the power of my polynomial, so it cannot be negative too. So the polynomial that I choose as the solution, right? So if n is equal to 1, I have a 0th order polynomial, which is just a constant, and I need to have L equal to 0. The only solution possible is to have a spherical harmonics with L equal to 0. And by the way, if the spherical harmonic is like that, n can only be 0 as well, right? So there are now like several rules here. If I make n equal to 2, then there will be another rule here. Either j is equal to 1, then I have a first order polynomial, I still have an R function there, but L has to be equal to 0, or I can have j equal to 0, then I have 0 order polynomial, just a constant, and L is equal to 1. Now I have the spherical harmonics has L equal to 1, which also means that the theta part of this function is associated Legendre polynomial with first order polynomial for that coordinate, right? So this explains why when I have a hydrogen atom, when I choose the quantum number equal to n, then the quantum number L has to go from 0 to n. That's to n minus 1 actually, right? So this is what you get here. And the other rule for the quantum numbers, which is n, that has to be from minus L to plus L. This one comes just from the spherical harmonics and how they are defined. But now this thing here that connects the n, which is the radial quantum number, with the angular quantum number L, this is something that comes from the fact that I solved this thing with a polynomial, which is it's related to the fact that when I want to quantize these energies, the quantization of the energy here, it comes from the fact that I cannot have a polynomial with j, the order of the polynomial going to infinite. So these are all connected. These things are all connected to each other. Notice that this thing, when I have n equal to 2, for example, and now I have L equal to 0 and L equal to 1 as possible solutions, there is a degeneracy here, right? So this degeneracy is, I have two states with n equal to 2. If I have, and actually I have another degeneracy for different m's too, but this is something else. The other degeneracy is like, let's say n is equal to 3. Then I could have L equal to 0 or 1 or 2, and they will all give me the same energy. So this is this threefold degeneracy and the twofold degeneracy for n equal to 2 and so on. These degeneracies, they occur only for the Coulomb interaction. If you solve the problem the way I solve it here for the Coulomb interaction, then you get that. Otherwise, you don't have something like that. If you have just, let's say, just a sphere of V equal to 0, the potential going to being 0 inside a sphere, and the potential going to infinite outside the sphere, there will be no rule like that. You don't have a rule connecting n to L. But here in the Coulomb interaction problem, then you have it. Okay. So let's see how is the wave function now. Let's go all the way back to the wave functions. And my wave functions were something like I had this u, which was u of r, and I said it was something like e to the minus the square root of er, right? And then I have r to the L plus 1, and v function, which is this polynomial. So I will put just a v like that, but now it's a v of jl because it depends on what is the polynomial that I choose here. And remember that this is not even the actual wave function. The wave function is actually r, right? For the radial coordinate, I still have to put to multiply this by the spherical harmonics, right? But now this r of nl, it's going to be something like e to the minus square root of e. I will already rewrite all the coordinates in terms of these, like the coordinates with units. They will need to be divided by a0. Square root of e is going to be 1 over n. And now r to the l plus 1 over a0. Actually, remember that this r here, it's u over r, right? This big R, the capital R, is actually u over small r. So this r here, it will cancel this one here. This will cancel this one. And now I have just a0 to the l in the bottom here. And the polynomial is v of jl that I put here. So for example, let's say that you have r of 1, 0, right? I want to see how this is. This is going to be an exponential minus r over a0, because n is equal to 1 here, right? L is equal to 0, so I don't have the r coordinate here. And the v, which is the polynomial, it has to be a polynomial of order 0, which means just a constant. So this constant here will just be the normalization constant of my function. This is going to be what we call hydrogenic function. So this is a solution that is just, what I'm saying is the electron wave function is decays exponentially with r from the origin of the system, which would be the nucleus, right? So if I want r to 0, then what I have now is I have e to the minus r, n is equal to 2, then I have a 0 here. L is equal to 0, so I don't have an r. But now, if L is equal to 0 and n is equal to 2, then I have a first order polynomial for Vj, right? Remember that I have n equal to 2. This means that j is equal to 1 and L is equal to 0, or j is equal to 0 and L equal to 1. So this is what I get from this in this example here, right? So now this is going to be a polynomial. I'm not going to derive this polynomial here, but it's going to be something like a plus b r, something like that, over a0, right? And this is the r with a unit, right? Now with a dimension, I mean. If I put r to 1, which is also a possibility, then I have e to the minus r bar over 2 a0. Then L is equal to 1. I have still this r here over a0. But now L is equal to 1, which means that j is equal to 0. So I have a 0 order polynomial here. This is just going to be a constant in the end here. Let's say a bar here. It's going to be another constant that I put here, and this is the form of this function here, r to 1. So if you look at these polynomials here that I'm describing here, if you want to see what are the actual form of all these polynomials here, this is just a 0 order polynomial, of course, so I don't have anything here. But here I have a first order polynomial. This is what they call the Laguerre polynomials. These are the Laguerre polynomials are the solutions to the Schrodinger equation for the hydrogen atom, and this is what what finishes my analysis here. So in another video, I will make a better explanation about the not the radial part, but the angular part of the wave function, and that's it.